Michael for joining us. So today for the Robot Learning Seminar, we are joined by Dr. Michael Yip, who is an Associate Professor of Electrical and Computer Engineering at UC San Diego, where he is the director. Oh, today for the Robot Learning.
Sorry,
What?
sorry, my bad. All good.
Yes, we're joined by Dr. Michael Yip. Thank you for coming again. He's an associate professor, as I said, and he leads the Advanced Robots and Control Laboratory ARC Lab, where his group focuses on a variety of research agendas across robotics, autonomy, artificial intelligence, and machine learning. And so today he's going to talk to us about some recent work that his group has been doing. So thanks again, and the floor is yours.
Great, thank you. So let me just adjust this. Hopefully you can. All right, so thank you for the introduction. So today I want to talk about robot motion planning and what my lab has been doing in this field and trying to bring it basically forward from decades of classical research in like classical planning to a new neural network and deep learning techniques. Just a quick background about my lab at UC San Diego. So I run the Advanced Robotics and Controls Lab. Here we do kind of the whole gamut of robot robot perception, modeling, planning, and control. A lot of it is in manipulation, and that might involve things like robots that are operating, in the operating room to general manipulators to snake robots that you may not think are, manipulators, but they're in some ways, untethered long chain robot arm to also even autonomous driving. But today I'm going to be talking about the motion planning component. And for those who are not familiar with motion planning, it's basically methods, a collection of methods that coordinate an agent, or in this case, a robot's motion to go from a start to goal safely while satisfying all desired constraints. So in autonomous driving, that would mean, stay on the road and avoid collisions with things. And the idea of the planning component would be how do you get from start to goal in an efficient way? But there's also other aspects of motion planning that can come up, like digital design. If you're, designing a car engine, you have to think about serviceability and how do you get tools within certain areas to service them, or how do you assemble the product so that it can be assembled and disassembled without necessarily, having various parts collide with each other or damage each other. And of course, there's a whole excitement about humanoids and the question about how do you plan in unstructured environments is really important, especially when you don't have prior baked-in knowledge about what the environment might look like. Oh, and then of course, there's also a digital protein design and digital actors like in video games. Okay, so motion planning at a high level, there's the basic idea, and this is just a 2D depiction, is that you have a start and a goal, and you have some regions that you're not allowed to access. And the idea here is that you're going to start sampling around the environment and building up a roadmap for yourself of where you can access. And that roadmap can often look like either a tree branching out or a connected uh, non-directional like connected graph. Okay, and then if you search and you sample enough times, you will find a path, hopefully, that not only is, a feasible path from start to goal, you'll find hopefully the optimal path. In this case, uh, the length is minimized. And so there's a lot of, and then in higher dimensional systems, going from 2D to 3D, this framework of creating a graph can be expanded upon, where the graph is now being created in a n-dimensional space, where the n dimensions are the degrees of freedom of the agent. So in this case, with a 3-link robot arm, your graph appears in 3 dimensions, and you're searching in a 3-dimensional space. And all the obstacles and regions where you cannot enter, or it's undesirable to enter, they map over to this feasible space in some nonlinear way. Okay, and then so in this in the bottom right, you'll see that example of a graph being formed. This is using something called RRT, or rapidly exploring random trees, and it's finding the graph, and then when it sees it gets close enough to the goal, it will start moving. Okay, so this is a many decades old field, 4 decades at least, and the taxonomy of motion planning approaches, classical ones, are relatively varied, comprising grid search methods. You could technically lump in like optimization-based methods as like a short horizon planning planning approach. There's sampling trees, potential fields methods, and roadmaps where you create those graphs that you search over. And of course, there's numerous open source libraries available. Move It, OMPL is a great one, and more recently, there's been other ones from NVIDIA and other companies um, looking at introducing their own packages to the community. Okay, but in spite of all of these in spite of all of these solutions, there's still like a major challenge in the motion planning community, uh, which is dealing with uncertainty and dynamic environments, and being responsive and replanning on the fly. There's also the problem of tasks that are heavily constrained. And by constraints, we mean that in spite of there being ability to move around, there might be some inherent task constraints that force the solutions to must obey some very particular set of conditions that make sample-based planning very difficult, and I'll explain that in a bit. And then finally, also safety, time critical precision planning. And all of these contribute to several challenges that boil down to the fact that it will be hard to find a solution, and it will take a long time to find a solution. And that's because, generally speaking, classical planners rely on this sampling approach that requires heuristics to sample in the space very generally. And the more complicated your task is, the more those heuristics tend to become less advantageous and tuned to the task at hand. And the further thing is that if you're planning in these spaces, it's often not a direct path to the goal. So the greedy approach that you might be searching in, so straight shot path or some deviation from the straight shot path, may actually not land you in the right location, and it may get you stuck. So what has to happen right now in classical planning is that you have to, first of all, perceive the environment. Then you do this planning stage where the robot sits and thinks for a long time, sometimes, if it's a complicated environment, before it starts moving, because ultimately it cannot be sure that the greedy path is going to lead anywhere closer to the goal than the non-greedy path. So this might take, even for a 7 degree of freedom robot arm, it might take up to a minute or two. Okay, so it's actually pretty substantial in terms of planning time in complicated environments. And so while it's waiting, it can't really do anything. And then only afterwards will it start moving. And if the environment changes, it might be able to make small corrections, but if its entire path gets blocked off, now it has to redo that entire planning sequence. So when we were thinking about this problem about 9 years ago, this was kind of the state, this was basically what everything was doing. And we started thinking about how in biological systems, we don't really do this because we've kind of baked into our understanding uh of the environments, generally speaking, that we're in, and the possible approaches and ideal kind of pathways to the goal are not a, a broad search, but it's a relatively narrow search, and that's from experience. And instead of just thinking about the entire path before we start doing a plan, executing our plan, we actually just go ahead and start using this baked in knowledge. An example I use would be, if I placed anybody in a building and I asked them to go and find me where the restrooms are, they're not going to search in every room. Like if it's an office building, they won't search in the conference room. They won't search, in the middle of, room. They're going to be they're going to have some pretty good idea of the ideal path to start searching, and they're going to just start walking, right? And so instead of this approach from robotics, can we go from just our a perception of where we are to starting to move? And that's where we came up with the motion planning networks framework. And this would be the first time that neural networks were used with the motion planning for the motion planning problem. And the idea is actually relatively simple. You use encoder network that takes in your observations from the environment. In this case, we use point clouds, but truly you could use any kind of input representation. You encode that environment into a latent space, and that encoded environment is then planned upon with a neural planner. And the neural planner takes the goal that you want to get to, the current location, and it spits out the next step. Okay. So the planning approach is basically a recurrent one. And what you would do is that you would give the environment, it would start putting out, step by step, every location it thinks it should step into, and it's going to make a connection between them. And then it's going to evaluate the connection to make sure that you don't really collide with anything. And there's a small chance, because neural networks are not perfect, you're never going to get like 100% accuracy. There's a small chance that you might miss, you might shave a corner off. And then those become basically new places to start up a new program, a new planning problem from start to goal. And so this new start to goal then queries the neural planner, and it creates a new pathway. Okay. And then finally, we can do some optimization to try to make the entire path a little bit simpler. And one final comment would be that if the neural planner fails to find a path in these infeasible segments in a certain amount of time, you can outsource that segment back to an original planner, a classical planner, which has a much shorter distance to travel between, and it will end up accommodating for those gaps that the neural planner was not able to find in a short amount of time. Okay, so the example of what that might look like is here's three relatively gold standard classical planners. RT star is based off of randomly sampled tree search, but it's been optimized so that the path links and the tree branching is optimal. So from the start to the goal, all those red lines show, the optimal path to any of those blue dots. So that's gold standard. Bitstar is really, the top of the performance chart in terms of current highest performing classical planning. And you'll see that even with Bitstar, there's quite a lot of sampling of locations in the space. Whereas the motion planning networks, because it's learned a variety of environments, in this case, this would be 2D blockish narrow pathway environments. Even in randomized scenarios like this, it will be able to find almost a straight shot path without any searching. So this will obviously reduce the planning time between in many different environments, And when you compare both the planning time and the optimal path, it actually is significantly better, oftentimes order of magnitude better than the classical planning scenarios. Here's just an example of MPNet, which actually moves immediately, right, to the start and the goal of to the start point, and then in this case it picks up the duck and then moves it over to the other side. Whereas the classical planner can take several minutes to find a feasible path of sufficient optimality before it decides to move. And so the difference here is that we can make robots now behave in a very responsive manner. And whereas in the past, in these challenging environments, a robot basically would have stopped. If you've ever looked at any of the uh, DARPA robotics challenges back only a few years ago, robots would sit and think for a really, really long time. And part of that is part of it is a little bit of perception, but a lot of it is the planning as well. Okay, so a crucial guarantee for planners are that classical planning frameworks give a guarantee of probabilistic completeness, which is if a solution exists, the solver will eventually find it, and then probabilistic optimality, which is that the solver will find the global optimal solution if you give it enough time. Probabilistic completeness is actually really, really important to have because without probabilistic completeness, you will never be able to be sure to trust how well your planner is, because you can never be sure if it will search the possible solution space. Okay, the full solution space. So that's a really important guarantee, and we have to make sure that all of our planners, even the ones that are neural networks, have this guarantee. And in some ways, we are able to demonstrate this by using that hybrid approach where if a neural planner fails, you kind of fall back on the classical planners. And if you fall back on a classical planner, you inherit these probabilistic guarantees. Okay, so that's what I wanted to mention about that. This the advantage is in incorporating the neural planner is that you get to have much faster planning solutions in higher dimensions with limited memory and when you have limited time to find those solutions. Okay, so one approach that we can look at to make the planners a little bit more robust, so it doesn't have to rely so much on hybrid sampling, is this idea of using stochasticity in its output. And the easiest way to introduce stochasticity is to introduce dropout as a technique in the prediction stage of the neural network. So usually dropout's used in training for robustness, but in prediction, if you use dropout, instead of getting a single solution out, you get a distribution of solutions. And if you've learned the um, if you learn the output distribution well enough, you're basically getting probabilistic, probabilistic sampling of the likelihood of where the right path is. And using dropout in this case produces solutions that end up being very well directed towards from start to goal without having to deterministically say that it will always, it has to take a certain path. And therefore, in scenarios where it might graze an obstacle, this technique ends up helping significantly to keep the planner, the neural planner, relatively robust to those scenarios. We've been able to show constrained planning, motion planning on dynamically constrained problems. In this case, vehicle is a constrained non-holonomic vehicle. Basically, it cannot move in certain directions, like laterally. It has to find its plan in spite of meeting the dynamic constraints of the agent. And so we can show that we can do this in the way that we encode the action space of the neural planner. We've also been able to show that it's can be introduced into model predictive control framework. And so MPNet combined with model predictive control can solve these highly dynamic control problems, like toy problems in this case are like double pendulums problems, and dynamic quadcopter flying in obstacles. There's also other extensions of this work that go towards how do you plan for the sequence for parking, other questions about learning tree-based search that incorporate neural planning, other kinodynamic neural planners, and several more about this approach of neural planning can be extended to its use in graph neural networks, as well as other higher level planning, hierarchical kind of planning approaches like motion policy networks, where you have not just step-by-step planning, but you have some higher level primitive to plan through. Okay. So these are relatively unconstrained problems in the sense that in the search space, you're looking to find a solution that may have certain parts of the subspace be infeasible, but your search of the subspace, the search of the space is still in the same dimensionality of the original problem. And so when we talk about looking at task and motion planning, we start introducing the idea that the dimensionalities of your search space no longer match the dimensionality of the solution. An example is the task of cleaning a window, right? And so in this example, the task of cleaning a window forces the manipulator to hold its end effector on the pane of the window, which reduces the implicitly reduces the dimensionality of the problem. This robot might have 3 degrees of freedom, but by introducing this constraint, it reduces the degrees of freedom at least by a factor of 1. So if you think about it from a sampling-based theory perspective, you're going to be asking the sampler to give you samples in a high-dimensional space, but everything has to actually be feasible. The only feasible samples are the ones that land on a manifold. And theoretically speaking, in a continuous space where you have floating point numbers, the likelihood is 0. You will have 0 chance of these samples ever actually landing on the manifold. I kind of think about it, of the problem of interfacing here's an example in Interstellar where they're interfacing and trying to plan an approach between their vehicle and a space station. Okay, so how can we introduce these constraints in the neural planning framework? And this is, from our best knowledge, the first time language has been introduced. So we talked about the idea of the task introducing a lower dimensionality to the planning problem. Well, that task can be encoded in a language method. So if we can encode the task via language into a latent vector, that latent vector can inform the planning space, which part of that planning space is feasible or infeasible. And so if we combine that language-based encoder, such as in this case, opening the cabinet will encode orientation and a position constraint on all possible solutions. If you combine that with the scene encoder, which is, the point cloud, or in this case, the voxel representation of the scene, the stochastic waypoint generator, and then finally, the other, unique element of this is a metric of how far our waypoint is to the encoded manifold, that encoding being from the language-based encoder. We can come up with this constrained version of motion planning networks. And so in this framework, we basically have a forward pass that encodes these into a the observation and the observations, the language encoding into a neural generator that both spits out our plan, but that plan also will be used in an evaluation of how far we are from the how far we are from the manifold that we need to satisfy, and that distance then gets back propagated via a correction term, so that it basically tries to correct the output of the neural generator so that the next waypoint lies as close as possible to the constraint manifold. This approach of both training a neural planner that can learn to plan within a constrained environment, as well as a projection of its plans to satisfy those constraints during runtime, helps us learn really long sequences of tasks that require motion plans that involve a variety of constraints, both in this case, don't rotate certain open cups versus, opening the door that enforces some hinge-like constraint, and so on and so forth. So this helps us really to solve these problems and drastically reduce time from what originally would be quite several minutes and up to tens of minutes sometimes to sub-minute planning execution. And so this pathway led us more towards the idea of how large language models could help solve motion planning problems. This was largely done right up until and right before ChatGPT came out. And when it came out, we started thinking about, how can we integrate these foundation models in? And actually, one of our biggest motivations was from Facebook. This is their debtor framework. But the idea was that we were interested in was its idea of encoding the use of transformers to encode the non-local behaviors of patches in the scene and get a higher level understanding out from that transformer encoder and that non-local relational encoding. So I don't think I need to necessarily go into examples of what transformers do, but this idea of self-attention that transformers provide give you the same kind of idea that you might want in planning problems, right? The idea that it should know what are the influences of certain waypoints going towards certain waypoints in a planning space, and how it might affect where you came from, and also how it might affect where you are going. And compared to just pure recurrence, where you do that step-by-step approach, it has a much stronger capability to encode this higher level understanding. All right. And so how might this look like from a robot planning perspective? If we look at the LLM version of, sentence structures and how it learns the distance dependencies between different words in a sentence, can we look at the idea of the different dependencies between different waypoints in a space? And so that leads us to the motion planning transformers work. And so this motion planning transformers identifies the regions of a space that are relational to each other, and then it suggests that planning should be done only in these spaces for a start and a goal location. We're able to do this by taking our input map, our start and goals, and encoding them using a variety of uh, you know fully connected networks and positional encodings into a transformer encoding, and then basically the output is a map of region proposals that the solution must lie in. And so once the regions are identified, we can search with higher certainty and with less sample or significantly higher sample efficiency within these search spaces to find a feasible solution. So here is an example of a cluttered space with the traditional type of sampling approaches. And here is what if we took those traditional sampling approaches and we augmented them by introducing a transformer layer that told it where it should sample. Instead of sampling over the entire space, sample only in these regions. And we can see the efficiency drastically improves. The nice thing about this approach is that we are now introducing fundamentally visual language encoding into classical planners, where we're taking advantage of both sides of the research and the development. And the nice thing is that because of the behavior of transformers and how they're encoded, it's much easier to extend any of its findings, any of the models to training on different size maps, right? So for one model, you can train a transformer to accommodate a much larger variety of both map sizes and complexities. We can show this for, again, several different applications, including the navigation problem for vehicles. Okay, so this was nice, but we faced a problem actually pretty quickly which was that it works really well for 2D maps, and because all of visual language encoding has been done with, obviously, with 2D, how do you extend this to n-dimensional spaces, right? Not only 3D spaces, but n dimensions. And so this actually took a pretty long time for us to figure out. And it actually turns out that we were thinking about the problem in a slightly wrong context. So we were thinking about sentence structures and thinking about the way that the self-attention works and how different words must be linked together and the structure of that. But what we ended up realizing, and the key to it all that made this work for high dimensions, was we should focus more on the idea that these language models are really encoding language, and English language and any language in general, you implicitly know the words, right? And the dictionary, a dictionary for every language. And instead of thinking about this problem as how do you rearrange the words, let's think about it from the problem of what are the words. And so we came up with the next version of motion planning transformers, which is vector quantized MPT. In this case, we're looking in a high dimensional space for instances of common paths towards any start and goal point. And if we start finding that the robot keeps going towards certain regions, these basically encode, for lack of a better word, a word in this high dimensional space that seems to be more prominent. And the more we learn this dictionary of words, and in this case, like locations that the robot likes to visit, when it goes from any start to any goal, the more we can get encoded representation of the entire, search space of this robot in a relatively compact encoded um, latent space. So one question would be, what should you do to what can you do to make the encoding more understandable and therefore be usable to classical planers? And the idea that we came up with is that the encoded space should be captured by the idea of normal distribution. So we consider these dictionary of values, a set number of dictionary values, and we try to quantize that dictionary so that each word in that dictionary has both a mean and standard deviation. And this mean and standard deviation is in the n-dimensional space. The n-dimensional space here would be, the action space of the robot or the configuration space of the robot, depending on, where you're coming from. So if we are able to learn the possible encoded this latent space representation that is very understandable from a um, from a parameterized perspective, then we can start looking at constructing paths through this space while having while using the statistical parameters as a way to promote informed sampling. And what I mean by that is we can use the mean and standard deviations of these different vectors to help us with probabilistic sampling so that we find solutions in a more informed way. So in the second stage of decoding and solving a problem, you encode the environment into your environment encoder. In this case, we use PointNet++. And then we take that encoding, we match it with our starting goal position, and we pass that into our transformer with the dictionary values. And that transformer will tell us where the search of the path should lie within. And then with the output of the transformer, we can start sampling based on the mean and standard deviations of those different locations to find the correct path. Here's a 2D example of what that looks like. So as we plan from start to goal, which is color-coded, we see that the transformer tells us in 2D what the mean and covariance looks like for where it thinks the solution lies in. And this really helps us do better sampling within this space to find the right path. With this approach, we can solve complex problems in higher dimensional spaces much better than previous methods. And even with a relatively simple dictionary size. And the interesting thing is that this dictionary doesn't really necessarily increase linearly. It actually increases very marginally as the complexity of the environment increases. So in this 14-dimensional space, we're finding that it's really not so much, how high of a dimension you have to search through, but how complex the space is in general. And so this is actually really advantageous from a scaling perspective. We can start solving these problems that would traditionally take many minutes to solve, and we can solve them in seconds. Here's an example of like real world scenarios where the robots are able to, find paths within a start position that's a relatively narrow passage and a goal scenario that's relatively narrow passage, much faster than the fastest planning solution. Okay. And we can extend this as well to the constraint, solving for constraints. So the same idea that we use for doing projection operators, we can apply to the new motion planning transformers framework by taking all of our words and we can take those encoded word distributions and we can project them down onto the constraint manifold. And then we can sample in this modified dictionary space. And here's just another example of how we can get a significant improvement in solving constrained tasks when we take that problem, when we take our original um, uh, vector quantized method and we add this projection-based constraint approach. All right. So the future to expand the language of motion planning, we're thinking about, not only the generation of these words to sentences, but also, to much higher level task planning ideas. And the nice thing about the, huge improvements in language modeling is that suddenly the problem of task encoding, which used to be a very hard problem to solve, becomes a lot more trivialized in the sense that the language models have a very long chain, ability to generate very long chains um, of sequences that make sense. If I say ask a robot to get me, you know, uh, uh, get me a drink from the fridge, it can find all the steps in quite a lot of detail without making mistakes, at least in language form, of how it as a robot might go and get, a drink and bring it back. And that might be a very long chain of tasks that in the past would be very difficult to represent, but now is much easier. And then the final thing is that we've been working on these foundation models with other universities to encode what's been learned either via teleoperation or just straight up motion planning into neural planners. And this example of one of the foundation models on called Droid has been one that we had worked on. Yeah. Okay, and this is obviously in very general environments. Okay, so last like 10 minutes or so, um, or maybe a little less than that, I want to just talk about some applications of motion planning that we've done in the lab. One of them is planning for autonomous medical evacuation. We're looking at how robots can enter into these challenging environments and find casualties in either natural disasters or on the battlefield and try to extract them. A part of this problem involves doing motion planning under constraints because if somebody's injured or in a very awkward position, you don't want to have the robot execute a plan that further injures them. For example, if it doesn't know the biomechanics of the body, then it's very likely that it could do something that moves the joint in a wrong way. So part of this involves both body pose and weight estimation of a person that it sees in the natural environment. And then furthermore, executing a plan once it has defined the configuration of the person and finding a plan where that robot considers the biomechanics of the person in constraining the plans that it will do to reposition them and then pull them out of the scenario. Another application that we've looked at for like a very, very large scale planning problems is in medical space. In this case, it's for biopsy and lung cancer. We actually have robot that is going to live within the CT scanner, and whenever it sees a cancerous lesion, it's going to automatically plan a path to get to that lesion and pick out a piece of that tissue for sampling to see if it has cancer. This is just an example of some of the hardware that we do in the lab, which is, in this case, a robot that reaches into the scanner, has 10 degrees of freedom, so very high dimensional space. It has to plan itself through here, and then it has to plan a needle trajectory that goes in through the rib cage of the person, so avoiding obstacles, and then hitting a goal that's within that person's body. Here's just what that robot looks like at the end effector. It's all cable driven. Again, very high dimensional robot. And the problem there is to solve this in parallel so that the robot can execute the most optimal path, the fastest path in the least amount of time while the person's being scanned, because every scan you take involves radiation to the patient. Another problem that we look at is surgical robotic setup problem. And so when you set up a robot that has many, many degrees of freedom, but has to operate in a very tight space like the human body, you end up having a question of what is the best setup for this robot. And the way to evaluate that is really to take in all the knowledge that you had of the possible motion paths that the robot can move in, and encode that into metrics that say how much reachability or self-collision do I have amongst the large scale of paths that the robot may have to take. And to evaluate this in a reasonable amount of time, we need to use tricks to to evaluate these maps and get basically an idea of the ideal positioning of these high dimensional robots every time a new patient with different anatomy comes in and changes the possible paths between starting goals in the person's body. Okay, so just some examples of the way that it can evaluate good and bad solutions. Okay. This was this was a little bit out of order, but this is the idea from the previous robot where as it enters into the CT scanner, it has to evaluate its ability to plan through all possible locations in the person's torso where cancer may actually be, and position itself relatively quickly and in an optimal way to reach those lesions with the least amount of trauma to the patient. And we can evaluate this over many different patient anatomy and scales. Another application we've been looking at is safe manipulation and dynamic clutter. One aspect of working in an environment that has clutter is that things don't stay stationary. So let's say reaching into a fridge, you're going to most likely be, knocking into things. And the question is not that you should avoid it, it's to be smart about it. And so part of the planning problem is to understand and incorporate the knowledge that you've gotten via, intermittent movements and replanning on the fly. And so this idea of rapid replanning comes into play when you can determine how safe it is for an object to be moved, in this case, tipped over, and you just don't know what is the center of gravity of the objects because they may be filled with, in this case, these bottles might be filled with different volumes of liquid. And so via interaction, we can do like rapid replanning. And in this case, the innovation here is that the contribution and the novelty is that it turns out object-centric safety helps us do rapid replanning much faster and much more robustly, because even though the objects are dynamic and they can move, we can, if it's object-centric, we can flatten all the estimates of safety based on repositioning of where those objects are in the safety map, and we can have the robot replan quickly on the fly to accommodate for that. So after enough interactions with the environment, it finds out a safe path through it. Finally, one other application that we do, since we work a lot in medical robotics space, is to look at the problem of replacing doctors in various simple surgical scenarios. The reality is that there is a significant shortage of physicians and surgeons right now, and it's going to just get worse over time. And that's going to lead to longer wait times, surgeries canceled or postponed, and equity declining. And surgeons are very tired. They actually really welcome AI and autonomy to help them overcome, the amount of work that they have to do every day. And so we've looked at using autonomous task and motion planning to solve the suturing problem, and amounting to, demonstrations like this, where our robot can learn the encoding of what it means to do both constrained planning and open space task and motion planning. The constraint here is to follow, for example, the needle curvature um, through the tissue, and then the larger open space planning is how do you do robot object handoffs, where you have to avoid the collisions between the object and the different arms with the grasping arm. And we've applied that to problems of emergency vessel repair. So in summary, learning-based neural motion planners provide autonomous navigation and enable advanced dexterity in complex places. And the advancements in machine learning really are doing a lot to increase the scalability, robustness, and applicability of neural planning to new tasks. And there is a really, nice way that classical approaches and neural planners can help each other, both from an efficiency standpoint and a robustness and probabilistic certainty perspective. And so I think the path forward are that these two fields are going to both still contribute a significant amount to improving motion planning for robots in the near future. So thanks for your attention. These are just some of the students that have worked on these problems in the lab. And thank you to the funding agencies, and I'm happy to take any questions.
I guess I have one question. If no one else has one. I'm a bit curious about these neural planners, and if you could maybe talk a bit about like how do you train them? Because I guess one thought that comes to mind is maybe like you're kind of aggregating, I guess, all this prior knowledge about the world into the planner, and so then like how easy is it to generalize it to spaces you haven't done any planning or have access to good models for? Or is that a concern you don't really care about in the motion planning space where you, like how robust is a neural planner to trim like changes in spaces?
Yeah,
Like,
no, that's a really good question. So all the planning examples we showed already, they have been done with random environment generation from a perspective of not semantics, but there's no necessarily semantic environment encoding in there. It is really like uh occupancy, almost like an occupancy grid question. And so if we look at it from that perspective, randomizing the occupancy of an environment that surrounds a robot ends up being very, very generalizable, um, because uh, uh, you don't have that semantics in it, right? Once you start taking into account, once you start thinking about the semantics of the environment, then the distribution of what you can see becomes much bigger. I would argue that that's more like a task planning problem from the language side, right? And so the language encoding should tell you more about what the definition of certain constraints are. And that's kind of an open problem. Let's say, I need to grasp a bottle from the fridge. I don't think it's like a hard problem to overcome, but it's still an open problem. It's like if I want to grasp a bottle from the fridge, it can tell me that, okay, the sequence is move robot hand to pick up the bottle and pull it back out, right? And it should learn that you shouldn't dip the bottle and what that encoding should be. But that I think is that's more on the language side, and that language translation side. Whereas I think the problem of planning planning for that, as long as you have this occupancy map encoded, is much more generalizable.
So you don't, I guess, so then you haven't had any issues in your experiments of like taking a neural planner trained in room A and then applying it to room B kind of settings, if I'm following?
So yeah, so we've seen a buildup of that. So originally, we were having we didn't have like just enough compute power to very generalizably like vary the occupancy of the environments it sees. But then over time, especially with the introduction of like the transformer networks, and the fact that we didn't have to use uh um the encoding methods from 8 or 9 years ago, it's become much easier to have to train a very generalizable encoder for environments occupancy. So we've
Okay.
actually seen a lot of success there. I will mention one thing is that uh, one interesting aspect is that when you actually try to get expert demonstrations to train these neural planners, you actually have to rely on originally like the traditional motion planning approaches, right? So either you do that or you rely on teleoperators. So the collection of the data required to train the planner side of things, so the neural planner side, not just the environment coding, that actually takes some time. That's really the limiting factor.
I see, yeah, because I guess I kind of wonder if like the reason you have the benefit from the neural planner is because you've shown it a bunch of different trajectories and stuff, and so in my mind, you kind of, I guess, in some way, like memorize it all in the
Yeah,
neural
well,
plan.
so right. So the planners, because they're giving like waypoints in the environment, the each sequence in the environment is not just one data point. It's a ton of possible data points between one location to another location. So just solving one problem is not only like one sample to your training set.
I see. So it's really easy to get data to train these things then.
You can definitely leverage one trajectory in a significantly more like one trajectory equals many samples, basically. Yeah.
I see. All right, since we're going a bit over time, let's thank our speaker again, and thank you for joining us today. It was
Yeah,
really
thanks for the invitation. Okay. All right. So I'm gonna head off
Yeah,
then.
you can go. Yeah,
All right. Thanks.
yeah, thank you. Thank you so much. It was great.
Bye.
Bye. Wait, I guess we're still up. Bye, Liam. All right.